Enough, and that's honestly the hardest part is probably the review. The Algebra 2 stuff is not that big a deal. The Algebra 2 part of 5.3 is going to be this type of thing. What 5.3 represents is a different way of solving quadratic equations. Chapter 5 is mostly about solving quadratic equations. That's the big thing that we do. What you're going to learn to do, and what we're going to spend a lot of time with, is choosing the best strategy based on whatever the quadratic equation that you're solving looks like. We dealt with kind of the hard case already, which was the factoring case. In 5.3, we're going to look at the case where we've got a quadratic equation that we can see when we look at it. We'll talk about why here in a little bit. That we can see is easier to solve, and then we don't have to factor. We can use a different technique that's a lot easier. That's what we're going to talk about in 5.3. Okay. So the technique we're going to use is finding square roots. We're going to be able to just solve some quadratic equations by just isolating x, and in that process we're going to have to square root both sides. Okay, this is going to work in situations, in situations like this, for example. What if we were solving this, that is a quadratic equation. It's got an x squared in it, so it's quadratic. If I want to solve this, you guys know how to do this intuitively. You've done some stuff like this. You know, what do you do to solve that one? Square root each side. And this fits with the stuff that we've been talking about all year. If I can point to a single x, then I can isolate it. And in this case, I isolate it by square rooting. Okay, so if I square root both sides, the thing that you got to remember here that sometimes people forget is if I've got x squared equals 4, then I have to square root both sides, and I get x equals plus or minus the square root of 4, which is 2. Okay, anytime that I'm going to take an even root of both sides, if that's an even power of x, and I'm going to undo that even power of x by taking a root, an even root, a square root in this case, I always have to put a plus or minus in the answer. Now I'm going to tell you why that is, but in all honesty, you're probably going to, sort of semi-forget about this because you don't really have to know this every time. You can just skip always from here right down to your answer when you're solving quadratic equations. There is kind of an invisible couple steps in between there that look like this. What I do is I actually square root both sides, and so I get the square root of x squared equals the square root of 4. Now, the book, honestly, is sometimes, they do something that's not mathematically correct here, and almost every textbook does, and I think even this PowerPoint probably might too. They make the statement that the square root of 4 is actually plus or minus 2, and that's not true. The square root of 4, the primary square root of 4 is 2. It's just 2. Where we get the plus or minus from is this part right here. The square root of x squared. Now think what that's doing. The square root of x squared. Let's say I put in a number like positive 3 for x. Well, let's say we put in positive 2, how about it? So it fits this. If I put in positive 2 squared is what? 4. Square root of 4 is 2. Okay. What if I put in negative 2 for x? What's negative 2 squared? Positive 4, right? Negative number squared is positive. Positive 4 and the square root of 4 is? Now what does that sound like? If I put in a value of positive 2, it spits out positive 2. But if I put in a value of negative 2, it spits out positive 2. That sounds an awful lot like something we've dealt with this year already. What did that thing? What function did we deal with earlier that did that very thing? When I put in a positive, it didn't change it. But when I put in a negative, it made it positive. What do you call that? Remember? What did it look like? Describe what it looked like. What did that function look like? If I put in, now think about this, you're making this harder than it is. If I put in a positive number, the function didn't do anything to it. But when I put in a negative number, it made it positive. Absolute value, right? That's it, absolute value. So what this is really ends up being equal to is the absolute value of x. And if the absolute value of x equals 2, as we talked about way back in chapter 1, we know that x could equal either plus 2 or minus 2, right? So that's really where that comes from, okay? But, like I say, you don't have to do that every time. You can just, we know that that's what's going to happen, and so anytime we see an even power of x, and I'm going to undo that by rooting, I just know to put that plus or minus in front of the square root. That's our shortcut that we can always take. Okay? Questions on that? Okay. Okay. One positive and one negative. Can't forget that. Okay, so let's take a look. That's what we're going to be doing with this. Now let's just focus on just reviewing square root stuff for a little bit. So this goes back to Algebra 1 and maybe even pre-algebra a little bit. So we call this a radical, right? Square root of 3. This is the radical sign. Now something that we're going to need to be aware of in the future, so I'll mention it now, is that there actually is an invisible 2 that sits on that radical sign. That's what we call the index of the radical. That tells us what kind of root are we taking. A square root is really just a second root. It's undoing. It's sort of the. We know that how do I undo something squared? Well, I square root it. How do I undo a square root? I square it, right? So it's the inverse of a square function, right? Later on, not this chapter, but later on, when we move into chapter 6 and 7 and beyond that, we'll look at some other kinds of radicals where we have like cube roots or fourth roots, and then you'll actually always see that number up there that tells you what kind of root. If you don't see the number, it just means that it's invisible 2. It's implied. Okay, and then the whatever number is inside the radical, technically we call the radicand, but it's not that big a deal. Okay, properties of square roots. So first of all, we know that we cannot take the square root of what? There's 2 rules for real numbers. We can't divide by 0 ever, and there's one other thing. We can't take an even root, in this case a square root of negative. Yeah, you can't put a negative number inside a square root and get a real answer, okay? So we always have to make sure that whatever's under the radical is 0 or positive, meaning non-negative. So here's the product property. This is just, you would have guessed this. This just makes common sense. If I have the square root of a times b, I can split that up into the square root of a times the square root of b. And that's fine to do. Quick example of that. If I had the square root of, if I had the square root of, let's say, I had the square root of 36. I could break that up into the square root of 4 times 9, because 36 is just 4 times 9, right? And I could split that off into the square root of 4 times the square root of 9. What is the square root of 36? 6. What's the square root of 4?
2.
What's the square root of 9?
3.
Yeah, see, it works. Okay. You can always do that. Here, it wouldn't have been such a useful thing to do. Yes, ma'am?
There's some, like, it's 38 and it doesn't square right?
Say that again?
Like, it's the square root of 38 or whatever, and you do the 4 times whatever.
Right, that's...
It doesn't square right?
Yep.
Don't you put the single number that squares outside and then the square root?
Exactly, and that's the next example I want to do. In this case, we wouldn't really necessarily have to use this very much because 36 was a perfect square to start with. That was just a waste of time. But what if the number wasn't a perfect square to begin with? And this is why we have to use this product property. This is where it comes in handy for us. What if we had something like this? If we had, say, the square root of 50, right? Now the square root of 50, is there a perfect square factor of 50?
No.
Meaning, now think of the perfect squares. Perfect squares are just numbers squared. So 1 squared is 1. Now we don't worry about that one. 2 squared is 4, so that's a perfect square. 3 squared is, okay, what would the next one be?
4 squared is
16. 5 squared is,
25.
and then with 36, and we just keep going. Is there a perfect square that divides evenly into 50?
Yes.
25 does, right? So we could split the square root of 50 up into the square root of 25 times 2, which is really just the square root of 25 times the square root of 2. which is equal to what? What's the square root of 25? 5. Okay, so 5 times the square root of 2, or 5 radical 2, whatever you want to call it. So our goal, when we're simplifying square roots, is always to get as much outside of the radical as possible, but typically we're going to get stuck with something in the radical. The way we do that is this process. You want to just think, now, what's the biggest perfect square that divides into this? We're going to split that number up into the product of the perfect square and whatever's left over. And honestly, you can just skip this step. Just skip up to that step right there. Okay? And then, you know, we turn the square root of the perfect square into just a whole number. Done. And then we're stuck with whatever the other part of that factor was. The other factor was. Okay? And well, you'll get practice. There's a lot of problems like that on the assignment. Lots of practice with that. Okay, quotient property, same deal. Same deal. If I've got the square root of a quotient of two numbers, then I can split it up into the square root of the top divided by the square root of the bottom. Same idea. Okay, and then here just an example like we just looked at, square root of 40. Well, 4 goes evenly into 40, right? So I can split that into the square root of 4 times the square root of 10, and the square root of 4 becomes a 2. So I'm still stuck with a 10 inside the radical, but I got some of it outside. I'll show you another calculator trick for finding perfect square factors like that one I showed you. Remember the y1 equals a number divided by x. I got another one like that that helps you find factors that are perfect squares. So I'll show you that a little later. Same kind of thing here. I can take the square root of 3/4 and break it up into the square root of 3 on top, square root of 4 on the bottom, and then the square root of 4 on the bottom just turns into a 2. Okay? All right, so some examples. Try that one. Now, you don't even have to write it down. Just see if you can think about it. How could we simplify that radical? What's going to be the biggest perfect square that divides evenly into 500? And if you don't get the biggest one the first time, that's okay, because whatever's left inside the square root, you can just do it again. What do you think, Mary? Okay, so what was the biggest perfect square that divided into 500? Well, let's just say it again. What was your answer? 10 radical 5 is right. Okay, so 10 is the square root of what? 100. Yeah, 100 divides evenly into 500, and 100 is a perfect square. That's 10 squared. So we could split this up into, let's jump right to this step, right? The square root of 100 times the square root of 5, and the square root of 100 becomes our 10. Okay? And then we can always check and say, okay, now the square root of 5, is there a perfect square that goes into 5? No, there's not. So we're done. All right. Okay, what about this guy? What if I have something like 3 times the square root of 12 times the square root of 6? Now, there's a bunch of ways you can do this, but one way that's pretty foolproof, and you might decide later on you want to try something different. I could just combine those radicals. The square root of 12 times the square root of 6 just turns into the square root of 72, right? And now I'm just going to do the same thing that I did in example 1 to the square root of 72. What's the biggest perfect square that divides into 72? Okay, what do you think? 9 works. Okay, let's try 9. Let's see what happens. If I use 9, I could break that up into 3 times the square root of 9 times the square root of 8, right? And what's the square root of 9? 3. So I get 3 times 3 times the square root of 8 is 9 times the square root of 8. But now we better pause and ask ourselves, is there a perfect square that divides into 8?
4 times 2.
4 does, yeah. 4 times 2. So we could go again. We could say that's equal to 9 times the square root of 4 times the square root of 2. And what's the square root of 4? 2. So we can just replace that with a 2, right? 9 times 2 is 18
radical 2
times the square root of 2. Okay? Now, could we have done that in one step? Yeah, we could have. We could have actually found a bigger perfect square that divides into 72. What would that have been?
36.
Yeah, 36. Okay, but that worked, didn't it? I mean, like I said, you don't have to get the biggest one the first time. It just means you're going to have to do more than one process, go through more than one step. Okay, so here's, if we had seen that that was the square root of 36, we could have just turned that into 3 times 6 times the square root of 2, and there's our 18 radical 2. Okay? What about this? Square root of 25 over 9, just split it up. Square root of 25 over square root of 9. Square root of 25 is?
5.
Square root of 9 is?
3.
There we got it. Okay. Okay, now sometimes though, when we do that, like that last example, we end up with a leftover radical in the denominator. Honestly, that is not the end of the world, but most math textbooks seem to think so. And so we go through this process called rationalizing the denominator, which means we have to always get square roots out of the denominator if we want to have the answer be perfectly simplified. We don't want to ever leave square roots in the denominator. So there's a really easy trick for this that you probably remember. It's okay to have square roots in the numerator, by the way. Denominator, no way though. Okay. So if we're going to completely simplify it. So to rationalize the denominator then, we are just going to do something like this. Okay, say we've got the square root of 25 thirds. Split it in, just like before, we'll split it into the square root of the top divided by the square root of the bottom. Square root of 25 works out great. What's that? 5. Okay, but the bottom we're stuck with because 3 is not a perfect square. So to get that square root of 3 out of the bottom, whenever you're stuck with a radical in the denominator, you always just multiply both the top and the bottom by the stranded radical. Whichever one is stranded in the bottom, just multiply both top and bottom by that, and look what happens. On the top, we just get 5 times the square root of 3. Now, what's the square root of 3 times the square root of 3? Yeah, square root of 9, right? And what's the square root of 9? 3. Okay, there's another way of thinking about that. That's okay to do. That's fine, but maybe this is an easier way to think about what just happened on the bottom. Yeah, on the bottom, what I've really got, if I take the square root of 3 times the square root of 3, anything times itself is just, by definition, that thing squared, right? So the square root of 3 squared, what happens to the square root and the squared? They cancel, right? So what we're just left with then is just our 3 on the bottom. Make sense? So that's why we do that. We're going to get rid of the radical by multiplying it by itself, by squaring it. And so we just end up with that. That's our answer. No more square roots on the bottom. Okay? Okay, what about this, guys? Square root of 2 11ths. Same deal. Split it into the square root of the top times the square root of the bottom. Nothing simplifies. But we're stuck with, we've stranded square root of 11 on the bottom, so what do we do to the top and bottom? Yeah, multiply top and bottom by the square root of 11. And then on the bottom, we're going to get what? 11. Okay, solves our problem. On the top, what do we get? What's the square root of 2 times the square root of 11? Square root of 22. I can't, right, because neither one of those is a perfect square, so I've just got to multiply those into one number, and I get that. Okay? Okay, so now back to solving quadratic equations. Okay, so now we've got a little practice with this. So what if I want to solve this quadratic equation? Now, right now, we only have two choices. Either we're going to factor to solve a quadratic equation, or we're going to isolate x. Which one do we do here? Isolate x. Much easier, right? I've got an x that I can point to. A single x, so I should be able to isolate it. Now, think what that means. Isolating x, what we always did at the beginning of the year, when we isolate, we just work backwards through order of operations, right? To isolate, we just do that. So what's going to be the first step then if I want to get that x by itself?
Plus 3.
Gonna plus 3? Subtract 3 from both sides? Okay, everybody see that? Okay. So first we're going to subtract 3, and that's just this add subtract step, right? Okay. Whoops, I don't want to do that. Yeah. Okay, so we did this. We can check that off. We added or subtracted first. Next step would be multiply or divide. So what are we going to do next?
Divide by -5.
Good. Divide both sides by -5. Okay, so that just gives me x squared on the left, and then negative over negative is positive. So we did the multiply divide. Okay, now what's next?
Square root of 12 fifths.
Square root. Now why is that next? Well, because we're undoing an exponent, right? Does that make sense? The squared is an exponent, and so we need to undo that by square rooting. So order of operations just tells us to square root. So what's our answer going to be then? X equals what?
2.
Is it the square root of 12 fifths? No. I forgot something important. Well, sure. Okay, but okay, and we'll get to that. But before we even get to that, if I just said x equals the square root of 12 fifths, I'd be wrong. What am I forgetting?
Oh, you have to do square root of 12, square root of 5.
Right. Okay, and we will do that. But there's something else. Before I even start thinking about that, there's something important I forgot there. Plus or minus, right? Because I'm square rooting both sides of an equation, so I have to get that plus or minus in there. Okay, now why did they not have it there? They should. Oh, hang on, here it goes. There it is. Now, that's really not, I'll tell you what, let's forget this. I don't like, that's not as good. We'll do it, we'll just write it out. Yeah. So,
No.
so if I square root both sides, I'm gonna get x equals plus or minus the square root of 12 fifths. Now let's simplify our answer, but you can't forget that plus or minus, right? So then I just get x equals plus or minus, what do I do to a quotient, square root of a quotient? Square root of 12 over square root of 5, good. And then I gotta get rid of that square root on the bottom, right? Good. Square root of 5 over square root of 5. So on the bottom I get
Nothing.
5, good. Solve the problem.
6.
Square root of 60, okay, and what's the biggest perfect square that divides into 60?
6 times 10.
Yeah, but neither of those is perfect square, so let's just go through the list. 4 does, right? 4 divides into 60, does 9? No. We'll just go down the list. After 9 comes 16, does 16 go into 60?
No.
Does 25 go into 60?
No.
Okay, and then the next one is, now, it is 36, but now listen to this, this will save you some time, everybody pay close attention to this. If I'm going through my list, once I get past half of that number, I'm done, right? Because 36 is more than half of 60, and so obviously 36 can't divide evenly into 60, nor can anything bigger than that. So we can narrow this down. We're only looking for perfect squares that divide into half of that number or less, right? So it'd be, in this case, what, 4 times, how many times, 4 was the only one that worked. 4 times what is 60? 15. So I could write that as plus or minus the square root of 4 times the square root of 15 all over 5, and the square root of 4 is
2.
2. Good, so we get plus or minus 2 radical 15 over 5. That's my answer. Okay, what about this one? Okay, we're going to do the same thing. We're going to go through order of operations, reverse order of operations, right? So we isolate x by going reversing order of operations. So the first step is, now let me point something out here.
Plus 2.
What's the very last step? Parentheses. So I can't get to any of this stuff inside the parentheses until I get clear up to there. So outside of parentheses, do I need to add or subtract anything to both sides? No,
You have to
I don't.
But you can divide by 3.
divide by
Okay,
3.
good, but then the next step I can divide both sides by 3. Good. So let's do that. If I divide both sides by 3, the 3's cancel.
You have x minus 2
Equals 21 over 3 is 7. Good.
Now you do minus 2.
Okay, not yet, because I don't get there till I get to P, right?
Okay.
Okay, good. Exponents. I've got that square there. So I got to square root both sides.
Square
So you
root.
have x minus 2 which is square root of 7.
Okay, so x minus 2 equals, what about this side?
Square root of 7.
Almost. What'd we forget?
Get the square root of x.
Plus or minus.
Yeah.
Good. Plus or minus square root of 7. Good. Okay. Okay, so now finally we get up to parentheses. Last step is parentheses. So when we get to parentheses, we can just erase them for one thing. We can ignore them. So I didn't even really have to write them there. So let me erase. Oops, that's not what I want.
Oh boy.
Yeah.
Plus 2.
Okay, yeah, and inside parentheses, the last thing to do is just add 2, right? So I'm going to add 2 to both sides. Now, this is another step. Pay close attention to this, because this makes it easier. Now, I see some people not with me here. Jack, wake up. Pay attention to this. This is a good one. You're going to need this. So if I add 2 to both sides, I get x by itself. Now, on this side, I get plus or minus 7, square root of 7, plus 2. Here's a good trick. Always, if I'm adding or subtracting something to both sides, subtracting is just adding a negative. Always put that number in front of the plus or minus. And I get the answer 2 plus or minus the square root of 7. Both answers are there. One of them is 2 plus the square root of 7. The other one is whatever we get when we take 2 minus the square root of 7. Okay?
Ah,
See?
yeah.
Pretty tricky, huh? Okay. All right. Okay, so
Get
let's
those yellows over there. PSA.
more examples.
Minus 2.
Okay, what about this one? If I want to
Oh,
now,
this time
you always wanna
plus
look-
6.
can I point to a single x?
Yes, right there.
Isolate it. So what's first step?
Plus 6.
Add
Finally,
6.
Get it right.
Add 6.
Yeah.
So I
Then
get
you
4.
divide.
Now what?
Divide. I
By
can still
4.
see it.
Divide by 4. Whoops. And then
You square root.
square root. And what do I got to put from
Plus
square
or
root?
minus.
Plus or minus. All right. And then the square root of 12 I can simplify. Is there a perfect square that divides into 12? Okay. So I could split that into the plus or minus the square root of 4, which is 2, times the square root of 3. Done.
Winner.
How about it? Okay, last one.
Where'd that 2 come from?
Oops.
Square root of 4.
Square root of 4.
Oh.
Okay. Okay, what about this guy?
You have to divide 1 over 5.
Okay, I'm going to divide both sides by 1/5, but instead of dividing by a fraction, we always, good, multiply by the reciprocal. So I'm going to multiply both sides by 5. Good. Okay,
Oh,
And then you square root it,
square root.
which means
Okay,
then you can
Good.
take the parentheses.
Then you just add 4.
aha, okay.
Yeah.
Add 4 to both sides, so I get 4 plus or minus the square root of 30. Done. Because 30, no perfect square goes into 30, so I can't simplify that radical.
Aha, 15.
All right, you guys are getting this. Wow, this
I
is
really just said 15.
okay.
To the left?
Yeah. to the left. Let's go to 205. We'll get at least a couple questions in, maybe.
I just looked up my mom.
She's thinking of it. She was like,
To the max.
getting hungry.
Someone want to hit the lights for me, please?
Playing the lights.
Thank you.